kW is going to be small and much, much less than 1. And yes, it is 10 to the minus 14, a very small number. This is sometimes how the case of C is written for water, and it is such an important thing that it is written as kW. At 25 degrees Celsius, the kW is 1 times 10 to the minus 14. The equilibrium constant for water, like any equilibrium constant, is ridiculously dependent on temperature. 25 degrees Celsius is the current accepted standard room temperature. And actually, if you sit in a 25 degrees Celsius room, you discover that it's actually uncomfortably warm. But it's better than the old standard room temperature, which used to be 18 degrees Celsius, which if you were in that room, you'd discover was actually uncomfortably cold, the temperature of most rooms in England. Okay, so Sorensen came along and defined something as pH. If we have pH as equal to the negative log of the hydrogen ion concentration, this is the formula that you've all seen before. You'll say the negative log of the hydrogen ion concentration. And again, that's not what Sorensen actually said. He said it's the negative log of the activity, and that we deal with later. Again, concentration is close enough for our work right now. Why did he do this? Let's take a look at that kW. kW equals 10 to the negative 14. That is equal to the hydrogen ion concentration times the hydroxide ion concentration. When we're looking at the autolysis of water, the hydrogen ion and the hydroxide ion come out in equal parts. What is the hydrogen ion concentration going to be? They're going to be equal. The two of them as a product equal 10 to the minus 14. Give me a number. Exactly. It's going to be the square root of 10 to the minus 14. And the hydrogen ion concentration, therefore, is equal to 10 to the minus 7. Be able to do that on your calculators. Your next exam will have at least 10 of these where you have to calculate the square root of something. What Sorensen found out was that the hydrogen ion concentration in any solution ranges from 10 to the minus 2 and minus 1 to 10 to the minus 14 molar. These are small numbers. It starts with a small number and goes down to an even smaller number. And when working with numbers less than 1, is one without a calculator, without a computer, is one happy? How happy are you guys when you have to plug into your calculator numbers less than 1? Alright? You think having to deal with numbers like 1, 0 times 10 to the minus 14 on a daily basis, it is not a fun thing to do. And believe it or not, back then there was a huge body of math we were all taught, which was how to handle logarithms in a regular arithmetic way. And so, because he knew that all these numbers were just really impossibly small, and people didn't want to go 0.000000643 divided by 0.002476, right? This is not fun. But this is the sort of calculation that you would always have to do with numbers numbers in this range. So he said we'll just fit into logarithmic numbers. And in the particular case of something that has a concentration of 10 to the minus 7, so this is the hydrogen ion concentration of a neutral solution. In a neutral solution, water, you have hydrogen ion concentrations present at 10 to the minus 7, hydroxide ion concentrations present at 10 to the minus 7. You just said okay. The power on the hydrogen, pH, so the power on the hydrogen equals 7. And because this whole thing was because this is a very small number, he just threw that minus in here. Because what if he had simply said the power of the hydrogen equals minus 7, then we're dealing with a negative number? And nobody likes negative numbers. They're another thing that's difficult to handle, so we put the negative here, just so we could drop that negative there, and all our math is pretty, and that is totally and completely why he did it. This number tells us what is log of the hydrogen ion concentration, and now, if I have a pH equal to 2, what is the hydrogen ion concentration? So folks, get your calculators out. If you have pH of 2, what's the hydrogen ion concentration? Okay, you go back to your calculation, and you say pH is equal to the negative log of the hydrogen ion concentration. And so that was 7. So pH was equal to 7, was a negative log of hydrogen ion concentration. We want to solve for the hydrogen ion concentration here. We move the negative sign over. Negative 7 equals the log of hydrogen ion concentration. What do you do at that step? Negative 7 equals the log of the hydrogen ion concentration. What buttons do you press on your calculator? 10 to the, right? You're going to go 10 to the minus 7 equals the hydrogen ion concentration. Be sure on your calculator that you can hit those buttons. What if I tell you that the hydrogen ion concentration equals 4.7 times 10 to the minus 5. pH equals what? So you grab your calculator. I'm going to go log of this. And you're going to get some small number, right? So the pH is equal to the negative log of 4.7 times 10 to the minus 5. And what is that number? Sorry? Somebody says 4.33, or the same is at your end. Okay. Actually, the intermediate number, please. So simply the log of 4.7 times 10 to the minus 5. Negative 4.33. Everybody get that one? Okay. Note that when you have a small number, a number less than 1, the log is going to be negative. And so now, in order to get rid of that negative, the pH is equal to 4.7 connection with pH for neutral solutions, a solution of pure water. There's right here. Square root of 10 to the minus 14 is 10 to the minus 7. So in pure water, the pH is always 7. If you were to have a sample of water, pure water, and bring it out into this room and open it up to the atmosphere, keywords, open it up to the atmosphere. You measure the pH and it won't be 7, it'll be something like 6.5, 6.5. What goes wrong there? Suggestions? Carbon dioxide, as well as anything else in the air, dissolves in the water. And so you no longer have pure water. In order to get that value of 7, you actually have to have boiled your water to boil all the gas out of it. And then when you're done boiling it, you seal it under vacuum so that the gas doesn't get back in. It's actually fairly hard to do to get that really pure water and measure the pH properly. So note, if we have something that's acidic, the H3O concentration is higher. pH, negative log of the hydrogen ion concentration. I want to return to this slide actually. But note that when the pH is between 0 to 7, it's called an acid. And when the pH is between 7 and 14, it's called a base. And it will always be between those numbers because of the hydrolysis of water, and we'll get to that. We'll get to that in a bit. So then when they discovered this about acids and bases, they went and measured the pH, the acid content, the hydrogen ion concentration of everything. So this knowledge that the fundamental principle of an acid is that it delivers that hydrogen ion, or contains that loose hydrogen ion, is just from like 1900 something. Ammonia, household bleach, general chemical cleansers. Notice there's no fluids on the basic side of things. Fluids are either neutral or acidic. There are reasons for that. Note, the scale has the acid at the top, and with a pH of, say, 1. And we have ammonia near the bottom, with a pH of approximately 12, blood, and a pH of approximately 7.4. We have a scale here. And if I ask you which end is the, so let's say we have soda up here. This would be a really acidic soda. Which end is acid? Top or bottom? Top. You say acid. Cool. Which end is basic? Mm-hmm. And you say, yeah, what's my problem? Isn't that pretty obvious? I then, on an exam one time, had this scale written out like this. Soda, blood, ammonia. And asked which end was acid and which end was basic.